All right, so today we are arriving at a study of the Einstein equation. This is very exciting. We've done a lot of work to get here. Most of that work has all been mathematics, right? You can't understand the Einstein equation unless you understand all the differential geometry we've spoken about up to this point, with a few exceptions. You probably don't need to know much about the Weyl tensor, for example. But the point is to understand and appreciate the Einstein equation, you've got to go through all the differential geometry, right? It's just a hard process. Now, the thing that's weird here is this is all just mathematics, right? This is all reasoning and logic just done from foundational principles, basic axiomatic assertions and logical flow therefrom, a bit of different pedagogical strategies to teach it, a lot of notation, but it's very systematic. And we might expect that at this point, everything about this subject is systematic and strictly logical. But the Einstein equation falls into the same category as Newton's three laws. That is, the origin of the Einstein equation does not have a systematic history. There are those of us who are going to claim to derive the Einstein equation, but we're not really deriving it. What we're doing is we're trying to explain what it means. And explaining what something means once you have something to explain is actually easy. Coming up with this thing from scratch is very hard. But it's not hard because the systematic process to get to it is hard. It is hard because there is no systematic process to get to the Einstein equation. If you went to the history of Einstein's derivation, I don't want to say derivation because he didn't really derive it. He discovered it. I don't want to get into this feud about are these things waiting to be discovered or do they already exist? That's sort of a philosophical question that is very interesting. But Einstein, if you read sort of his biographies and stories about the way he thought, he stumbled in the dark for a long time before he landed on the Einstein equation. The ultimate expression that the Einstein equation is correct is always going to be experimental validation, right? And that's not true for the differential geometry, which provides the language to express the Einstein equation. That is all done through systematic logic. But the Einstein equation itself is a stipulation about physics, right? It's a stipulation about nature. And the only way to stipulate something about nature, well, you can stipulate all kinds of things about nature, but the only way to know which of those stipulations are correct is through experimental validation. Now, look, I'm not a philosopher of science here, so I'm not going to be pushing the boundaries on this because there's a lot of physics out there that is not experimentally valid, but is considered legitimate physics, of course. The more advanced and expensive the equipment needed, the more speculative our theories become. And certainly a lot of our cosmological theories, our theories about, fundamental fields and particles are getting into places that can't be experimentally validated, or at least not in the foreseeable future. But there's still science. The speculation, the process of speculation is science, whether or not experimental validation is possible, in my opinion. However, the Einstein equation, when it was created, experimental validation seemed extremely unlikely, although there was, of course, quite quickly the experiment done with the perihelion of Mercury, the explanation of that, but more importantly was the bending of light by the sun and all those things. But we're not here to talk about this at all. We're not here to talk about the experimental validation of this. We're here just to describe the Einstein equation from a modern perspective. How can we interpret what it's saying? But by interpreting what it's saying, it's totally different than providing evidence that it's true, right? The evidence that it's true is just, we've been working with this stuff for years and it's successfully, GPS satellites and Hubble Space Telescope and gravitational lensing and neutron stars that are spiraling into each other and goodness knows, LIGOs, measurement of gravity waves, all that is why it's right. the question is what is its mathematical structure and what is its mathematical statement trying to say? And we've set ourselves up so well that in principle it's a very short explanation at this point. So we want to discuss, this is the equation right here, as we've presented before. We want to discuss I'm going to say 3 parts. We want to discuss this side, which we covered in great detail in the last lecture. Then I want to discuss this side, at least enough to get a good grip on what it means and roughly how to interpret it, I guess. And then I want to understand this constant, which in different units is presented here. Remember, we always use G equals C equals 1. So our version of the equation is right here. I'll put a little red line around it. But you don't have to stick with those units. If you're in arbitrary units, meaning some units where this is not the case, then you have this guy right down here. Okay, so let's begin. The first thing that we'll just start with where we left off, basically, right? So the first thing we'll work on is the full contraction of G with V mu V nu, right? And we know if V is going to be representing our 4 velocity, they say the 4 velocity of a lab, then G is then G's full contraction with that, as we learned last time, is the curvature scalar of space-time in the manifold, the submanifold of our space-time that is orthogonal to our lab, right? So that's what the left-hand side says when you contract it with V mu, V nu. Now, obviously, we have to do this to both sides. So right away, we know that the curvature scalar of a submanifold, of an easily identified submanifold of our spacetime, that curvature scalar is directly equal to whatever this is. And of course, this is the differential geometry part, and this is the matter part. Well, I should say the matter slash energy part of the equation. So clearly this is that statement that space-time bends or space-time's curvature is defined by the matter, energy, and density. So now we've done this. Our whole last lecture was about this. So now we have to kind of focus on this thing. So we'll just do sort of a down and dirty description of how this tensor, this mass-energy tensor work. First of all, here it is in full expression, meaning I've included the basis vectors, which are these coordinate basis vectors, and this is the stress-energy tensor. Components, right? These are the components. So the first thing, of course, is to remember that T mu nu is a function on the space-time, right? That, like all these tensors, we're really talking about tensor fields, right? So this is a tensor field. And that's important because, right, what we have to remember is when we're looking at a space-time and we grab some, well, let's see, I better give it a full coordinate system here, right? If we grab some point on the space-time P, right, we're interested in what's the value of the components of the stress-energy tensor at the point P, right? What are these 4 times 4, 16 numbers, although this is symmetric, so I guess it comes down to 10 numbers. What are those 10 numbers? And so understanding the stress-energy tensor in space-time is knowing this field, which is knowing the value of the stress-energy tensor components at every point, right? I'm just saying, again, I'm really saying what a tensor field is. That's true for every tensor field, right? The metric tensor field, right, is mu nu. That's also a function of space-time. And the metric tensor field also exists at every single one of these points. So how do we use this thing? How do we understand how it operates? Well, clearly it is a rank 2 completely covariant tensor. So it takes 2 vectors. It consumes 2 vectors. So the question is how do we interpret what this machine, this tensor machine gives us? to use the words of Meissner, Thorne, and Wheeler's textbook. Tensor is a machine. What does it do for us? So the first way to think of this machine is that we feed the machine two vectors, right? A vector here and a vector here. So what if we put in one vector in the second slot? How do I know it's the second slot? Because I'm using nu, right? Nu is the second index, so that would imply the second slot. And if you put nu in the second slot, what you get is the density. This V is the volume. The momentum density. The momentum density seen by an observer whose forward velocity is u. So that's a forward velocity here, right? So when you put in a forward velocity of an observer, this is the output of the machine is a vector, or is a right. You can immediately see I did something wrong here, right? Because this guy contracts with leaves one down index, but this guy over here has one up index, right? So if we executed this up here would actually be the covariant form of the momentum, right? The covariant form of the momentum. Regardless, the four momentum, this is a four momentum. So remember, the first slot is energy, and then you have px, py, and z in the contravariant form. The covariant form, I guess you would have negative signs here. The point is just to remember, this is the four momentum we're talking about. This is the volume, so it's the rate of change of each component of the four momentum with respect to volume. So if I did this contraction using the forward velocity of an observer, what I'd be left with is a four vector that's the derivative of these expressions in covariant form with respect to the volume around that point in spacetime. And so, for example, I could find dp0 dv, which would represent dE dv, right? The mass energy. Or I could get dpx dv if I calculated t, I guess that would be 1 nu u nu, right? T1, because in this case, px is a stand-in for p1. I replaced the components of what would normally be p0, p1, p2, and p3 with these symbols here, just to give you a sense that we're talking about a little cube in space, right? This is Cartesian coordinates, for example. So the idea is that this stress energy tensor tells us this information. It tells us the density of energy at a point. You can't report what the energy is at a point because a point's too small, but you can report the energy density at a point, and that is what this is calculating. So that's very useful. Okay, so I just sort of rewrote that just to understand this energy density thing. Now, if it's a two-slot machine, right? So if I take U and put it into both slots, what I'm going to end up with is the projection of that energy, momentum energy density vector. Remember, this is still a vector, right? It's got a single index. The projection of that energy momentum tensor into the forward velocity of our lab frame. And that is basically just saying this is the mass energy density as viewed by an observer moving with forward velocity u, right? That is what that is. It's the mass energy density of the thing. So this is an expression of just pure mass energy density measured by a certain observer. And so that's really important, because what that says is, if we go back to this becomes the mass energy density of an observer moving at v with a forward velocity v mu. And this is the curvature of the submanifold of spacetime orthogonal to the observer's forward velocity. So the curvature of the spacetime orthogonal to the observer's forward velocity is exactly equal to the mass energy density that the observer observes, with this constant involved as well. And there it is. That statement is that statement. That thing's brilliant, right? Now, this, of course, can be done for an observer with any forward velocity. So these guys have to be pretty robust. I mean, they don't work with just one forward velocity, one particular one. They work with any forward velocity. So this machine ultimately has to be able to talk about the curvature of any slice of the manifold. And ultimately, embedded in it is the curvature of every slice of the manifold, because we know that ultimately this thing goes back to the metric, right? That's really no surprise. But the way the equation works is this guy depends on this guy, and this guy depends on the metric. So in principle, if I know this guy, I know this guy. And from here, somehow, I should be able to tease out the metric. This problem here is extremely difficult. It's only been done it's been done a finite number of times that are all well known. So starting from the mass energy density and getting to the metric is quite a challenge. Although we are going to do it in a minute, or in one of these, maybe starting the next lecture, maybe even this lecture. Okay, so that's the story of this, of the stress energy tensor and the Einstein tensor. What about this 8 pi? Can we clean that up? All right, so believe it or not, the rest of this lecture is going to be entirely about the old theory of gravity, because this 8 pi that we're chasing down, this number here, this 8 pi, where is it? This 8 pi, it's all about the Newtonian limit. This Einstein equation, which describes gravity, has got to, in the Newtonian limit, in the non-relativistic limit, reproduce Newtonian gravity. So we've got to do a quick review of Newtonian gravity and then execute this limit. And if you don't care about that, you're done. This lecture is over. But this 8 pi, I love chasing down these 8 pi's. I think that's a lot of fun. So let's do it. So the first thing is we want the gravitational field for a point mass, which is pretty familiar. It's the inverse square law. Now note the way I write this. The gravitational field is a force field. Is you take is a value in every point of space-time. So each point of space. Well, now Newtonian gravity is just space, right? So each point of space is given a little vector position. That's what this R vector symbol is. I'm now using vector symbols because we're back to like regular old physics. So, so this basic, this being the gravitational field, that means is if you multiply the field by a charge, you get a force. Well, the charge in this case is the mass of something that's in the gravitational field. So you might have a little m here, and then this would be the force on that object. Now, because mass and inertia are the same, it's much more interesting. This just gives us essentially the acceleration of an object placed in a gravitational field. It doesn't matter what the mass is because the mass cancels, right? Because force equals mass times acceleration. So ultimately, this is the acceleration of an object in a gravitational field. And that acceleration is given by this famous inverse square law expression, where g is, of course, the gravitational constant, m is the point mass, that's the source of the gravitational field. That's the source of it, right? The little m I'm talking about here is some object in the gravitational field. That's the source of it. ER is a radial unit vector pointing away from the source. R squared is, of course, the legendary inverse square distance factor. And then if you take ER and you treat it as a normalized vector of R, you sometimes see this with an R cubed in it. So that's for a point mass, but the gravitational field in total is this sort of integrated over every possible point mass. And that's usually written like this. Well, first of all, no, I'm gonna before we do that, which we will in a moment, this assumes that the point mass is at the origin. if you want to take this expression here and say the point mass could be anywhere in space, and I'm still interested in the gravitational field at a certain location in space where r is measured from the origin, all the vectors are measured from the origin, but if the point mass is located in r0, then you've got to rewrite it this way. And because the gravitational field is conservative, it can be written as the gradient of a potential. And we put in that minus sign because we want to show that this force is always towards, it's never repulsive, it's always attractive. So this is now the gravitational potential, phi, which is also a function of r. That r should be a little vector, right? Because of the way I'm undoing work that I've already done, I can't write the little vector in there. This is frustrating. But that is this is a scalar potential, but this is the gradient operator, which means this is a vector just like that is a vector. I love reviewing all these things. This is like physics, first year physics. Well, maybe not. Maybe this is more overall, this is probably more first semester physics, not elementary physics. Anyway, the point is it's been a long time since I've looked at this, so I'm kind of talking through it. But this is a vector, that's a vector. This, of course, this is a scalar, that's a scalar, but that is a vector. All right, so that's for a point mass located at the position r0. Now, for a mass distribution, we change this up a little bit. What we say is we still say, the gravitational field, it is still the gradient of a potential. But now what we do is we integrate over all space. So this is a vector. ds is a vector. We're integrating over the entire possibilities of vectors. And instead of integrating the mass, we're integrating the density. So it's the density of a certain region of space multiplied by this thing, which is effectively this statement right here. It's the it's the inverse square law, right? So now if we have points all over space and we integrate all over space, we're going to catch the mass of each of those points. All right, so that's the gravitational field for a mass distribution. So this is a more general application of this. Well, this is the integrated form of this when you have lots of mass. Okay, so what's next? Then I can take the divergence of both sides. So what's important? The next step is important. We take the divergence of the gravitational field, which ends up being the Laplacian of the potential, and that divergence just slips right through the integral. Now the divergence is with respect to r, right? It's a vector derivative with respect to the radial position. S is not r. This variable that we're integrating, again, I'm missing a little vector symbol here, but S is not r. So this divergence doesn't affect rho, but it does affect this object right here, right? So now I'm taking the divergence of both sides, and what this gives us is the divergence of this object here is well understood mathematically to be equal to 4 pi times the delta function of r minus s. Now, I'm not expecting you to suddenly remember that. I vaguely remember how that worked, and we're going to review it because this is where 4 pi appears, right? So 4 pi shows up right at this spot. When you take the divergence of this thing and you call it the delta function, that's where the 4 pi shows up. And ultimately, that's where the 8 pi comes from, right? It comes from this step right here. So we kind of want to study that. We want to make sure we understand why is the divergence of this thing 4 pi times the delta function, right? So let's see. Moving on with the assumption that that is the case, this delta function, when integrated over the full volume, just picks out r in rho. So you get 4 pi g rho at r, right? And then ultimately you get these two expressions right here, where you get the divergence of the gravitational field is minus 4 pi g rho r, or equivalently the Laplacian of the gravitational potential is 4 pi g rho r, right? So these two expressions ultimately are what we're shooting for when we're looking for the Einstein's equations reduction to classical physics. These guys loom large, depending on how you choose. They're the same statement, right? Some textbooks target this one, and some target this one, right? But they're clearly the same. But this is where the 4 pi comes from. Well, this is where 4 pi comes from, and ultimately 8 pi can be traced to this thing. So let's get a bit of a grip on this relationship right here. Let's see. Where did I... Okay, so we're interested in understanding a little bit more the divergence of this thing. This is a bit unsatisfactory in the end, in my opinion, but it is what it is. The divergence of this object is what we're after. We're going to do it in spherical coordinates, right? Because this is a spherical R vector. Spherical coordinates is clearly the way to go. So I'm writing the divergence in spherical coordinates. So this is how the divergence is taken of a vector in spherical coordinates. So the vector has components vr, v theta, and v phi in spherical coordinates. So the Laplacian is this long expression. To derive this expression, you have to go back to just the conversion from Cartesian to spherical coordinates, and it's just a coordinate transformation, really. But this is sort of legendary. I have to assume that you've seen this before in quantum mechanics and electromagnetism. But anyway, that's the divergence. Now, clearly, if we're going to take the divergence of this, v only has one component, and that's the r component, and it's 1 over r cubed. So derivatives with phi and derivatives with theta and derivatives with phi, those are just going to be 0. So ultimately, the divergence of r guy is just this first term. So it's 1 over r squared, the partial derivative with respect to r, of r squared times our function, which is r over r cubed. And well, there you have it, right? That is 1, right? R cubed over r. It's r cubed over r cubed, which is 1. So the partial derivative of a constant is 0, and that's what this is. This little stick here, that doesn't belong. So the divergence of this thing calculates out to be 0, right? Which is a bit of a puzzle. And the reason it's a bit of a puzzle is because of the divergence theorem. Well, maybe before I go on, I should wrestle with this a little bit, right? R is a vector here, right? Ultimately, 1 over r cubed, that's a scalar, but r is a vector. So our vector v is completely embodied in this thing r. Well, the r component of the vector v, right, is going to be r over r cubed times the unit vector in the r direction, right? But we don't care about the unit vector in the r direction. We only are interested in the component in the r direction. So that's why this r vector kind of just turns into a regular r, and you get r cubed over r cubed. Okay. So the next step is to sort of look at the divergence theorem. The divergence theorem tells us that integrating a divergence over a volume is the same as integrating the vector over a surface that contains the volume using this dot product, right? So you're interested in the unit normal to the area dotted into the divergence. Integrate that over the surface. You should get the same number as integrating the divergence throughout the entire volume. So if we apply the divergence theorem, we've already kind of calculated the divergence at 0. So the problem is this side is 0, but this side's not going to be 0. Right? This side, well, this surface volume, so let's substitute in our thing. So here's our divergence, which we kind of just calculated, right? That's what that is. Integral over the surface of our vector dA is ER over R squared. Here I've now taken I've returned to the unit vector formulation, right? So I've absorbed one of the R's into this vector R, and we get the unit vector in the R direction, right? So, and then that is dotted into the normal of the area element. Well, that normal of the area element in spherical coordinates is given by, if we choose a sphere, right, around the origin, the radius of that sphere, right, times sine theta, d phi, and then this dot product here becomes dotting into the unit vector in the r direction. But that dotted into that's the vector on this side of the dot product, and that's the vector on that side, so those two just become one. But you're on a sphere, so r is always going to be capital R, the size of our sphere, so these two are going to cancel because there's only one possible value for r. R doesn't change, it's not part of the integral. So this value of r is equal to this capital R. The capital R is the size of this arbitrary sphere around the origin that we're executing this volume and surface. So those two cancel, and therefore you end up with just the integral from 0 to pi of sine theta d theta and 0 to 2 pi of d theta, and that's 4 pi. So you end up with 4 pi on this side, but you kind of end up with 0 over here, right? Because this is a 0 term. So the way we've resolved this is we say, oh, you know what? This function is really weird. This function is actually the delta function. And this is a discovery of mathematics or this is the physics requirement to understand the delta function. This thing exists in the integral because all of the divergence of this function here happens only at r equals 0. And that is what causes the problem with this divergence function. So we have to invent this delta function to solve this problem. So we have 4 pi times the delta function. In order for the divergence theorem to work, we introduce this delta function, and and so therefore, ergo, this implies that the divergence of our function here, of our unique function, is 4 pi times the delta function. The delta function comes in here to actually capture the divergence of this thing, which only exists at r equals 0. See, this divergence is this divergence is a vector. This divergence is a number at every point in space, but it only has a value at the point 0, and that's what's so tricky about it. So to mesh it with the surface integral, which is plain as day 4 pi, that's where this factor of 4 pi comes from. Okay, so that's why this guy is 4 pi with rho of r, right, where we've absorbed the delta function, because here it's happily living in the integral where it belongs, so it can actually pick out this value of r for the density function. Let's see if I have anything else in here. Okay, so that is a review of Newtonian gravity, and the things to remember right now are these two guys right here.
All right, so let's now go on and try to figure out the Newtonian limit of our theory, and we're going to use that to figure out this constant. So we have motion, we have theories of motion that work in Newtonian theory and in GR. So the first one that comes to mind is that the motion of a particle, right, that's what this is, the acceleration of a particle, which of course can always be integrated to get its full motion. But the motion of the particle is given by a vector function x, which is some function of time, right? That acceleration is given by, as we've just worked through, the gradient of the potential. Now I'm adding a little vector bar over the gradient symbol here, because sometimes you see it, so you know how I like to constantly change up my notation. But also, because I can't make this boldface very easily, I suppose I could. Well, I'm not going to. So because I can't make it boldface very easily, I'm going to add that little thing. So we know that this is a vector on that side, the point being. But this is how a particle moves in a gravitational potential in Newtonian theory. Right? If I know the potential in all space, this is a function of space, right? Phi is a function of space. It's actually a function of space and possibly also time, right? But if I know this gravitational potential is a function of space, then I can calculate the motion. Now in general relativity, how do we calculate the motion in general relativity?
Well, we use the geodesic equation, right? The geodesic equation. And you'll notice that the geodesic equation, the world line is what this means, x sub I, where I goes from 0 to 4, four-dimensional manifold. The world line is parameterized by tau, and it equals this expression. Remember, typically in the geodesic equation, we have a minus sign here, and we set it equal to 0, but this is the same thing, of course. But the geometry of space-time is embedded in these numbers right here, the connection coefficients, and these derivatives of the world line with respect to its parameter contract into this connection coefficient, and that tells you how these, and ultimately that tells you how these coordinates change with time, or change with the parameter, right? Change with the parameter tau, which is usually taken to be the proper time of the particle. So these are two expressions that offer the same information, right? How does a particle move in the presence of gravity? Newtonian, it's a gravitational potential, and in general relativity, it's the curvature of space-time, the geodesic equation, and this, I don't know if there's a name for this equation, but this thing, right? The point being is that in the non-relativistic limit, and that's a complicated concept, like what is the relativistic and non-relativistic limit of something? But in the non-relativistic limit, this has got to reduce to this, right? And that's the hardest part of this lecture. We're going to spend more time studying that than we did deriving the core element of the equation, that curvature of a slice of space-time orthogonal to a certain observer is equal to that observer's view of the energy density of space-time, right? So right there we have sort of the plan. We've got to show that the guy on the right is the same as the guy on the left. Another possible approach is to look at this from the view of the potential equation itself, right? These are other true statements. Just like the motion of a particle is determined by a potential, the potential is determined by the density, right? So this is a function of space. Rho is a function of space. This is just a constant, and we know how this constant came about because we kind of worked through that. But this is the function of space, and we know that the Laplacian of the potential equals that thing. And this is simply another version of this, right? This is just a restatement of this in a one step back, where I guess we're taking the divergence of the gradient of G, right? The gradient G is the gradient of the potential, and the divergence of the gradient is the Laplacian. So this is the divergence of G, which is the gradient of the potential. This is the same thing. You introduce a minus sign. That's about all. But what's the general relativistic equivalent of that? Well, that's the Einstein equation, right? The Einstein equation is the field equation of general relativity. This is the field equation of Newtonian mechanics, right? So this has to reduce to this as well. So there's these two approaches. This can reduce to this can reduce to this, right? So in order to make this work, we need a few assumptions. So let's list the various assumptions that we're going to make. And I guess these assumptions are what we mean by the Newtonian limit. What is the non-relativistic limit of things? Well, the first sort of obvious one is the fields have to be weak, right? We're not expecting Newtonian theory to capture black holes, spinning black holes and crazy stuff, right? So the Newtonian fields have to be weak, right? But weakness, this is unscientific, right? This is not mathematically useful to say the fields are weak. We're going to have to figure out a way to define what we mean by a weak field. This is also true here, right? These guys represent the field in GR, so they have to somehow be weak, right? So if this is the field, the gravitational field in a sense of GR, if ultimately it's buried in here, something in there has got to be weak. So we're going to keep an eye out for how we can assert weak fields. But that is an assumption that I think everybody can assert that we need to make. The reason we know that there's something there is because Newton's theory doesn't predict black holes, for example. So clearly there's a point where fields get so strong that this is not a viable theory anymore. So we're going to keep an eye out for weak fields as our first assumption. The next assumption is that things are moving slowly, right? Now here we can actually say what we mean by this. Everything's got to move well below the speed of light, right? Much less than c, right? Wow, that looks like CCC, doesn't it? Hold on. Less than c, right? Or really we should be saying less than 1, because in our unit c equals 1. But things have to move slowly. And what's actually interesting about this is that Newton's theory really doesn't care how fast things move, right? The potential field is determined exactly by the position of all the mass, and its effect on a piece of matter located in a certain place doesn't really matter. It only cares about the instantaneous arrangement of matter to create gravity. That's one of the fundamental obvious problems with Newtonian theories. Rapidly moving matter, right? Rapidly moving matter is going to change the fields very quickly, but those changes are going to be instantaneously felt by test particles floating around the matter that's generating the gravitational field. That's one of the fundamental kind of curiosities about Newton's approach, is that gravity acts instantaneously. But what's kind of interesting is that we might ask the question, well, what if we have really weak fields, but things are moving quickly? And there's still a problem there, because even if you had a really weak field, if things are moving fast enough, there's probably going to be a problem in Newtonian theory. Or Newtonian theory is basically, if Newton's laws is only about so-called weak fields, it's still true that if things move very, very quickly in Newton's theory, things will be instantaneously affected. But GR, even if you have weak fields but things move fast, you're going to get gravitational radiation, regardless of how weak the fields are. So there is this little tension between weak fields and things moving slowly. They both must be enforced separately. You have to have weak fields and things have to be moving slowly. Okay, so those are two assumptions we're making. The third assumption is that the fields are stationary. Now, I kind of just talked about this, right? When I say things move slowly, the fields are, so there's two things in the universe, right? The things are, say, planets that are producing gravity, right? So those planets must be producing weak fields, first of all. They have to be moving slowly, because if they're moving quickly, then the fields are going to actually change, right? So the things that are moving slowly certainly have to be these planets. They have to be moving so slowly that the fields themselves don't change at all during the amount of time we're interested in, right? So the fields are stationary, which means this field here is not a function of time in the Newtonian limit, right? The fields are stationary. The other thing that can be moving is the test particle, right? There's always this test particle, which actually could be a planet, right? These might be giant stars, and the test particle could be a planet, or they could be planet and the test particle is like a little satellite or something. But the test particle also has to have a velocity well below the speed of light, right? So otherwise Newton's theory isn't going to work very well either. In other words, and the problem there, of course, is that the accelerations aren't going to make sense, right? Newton's law will allow you to accelerate straight through the speed of light, right? So we don't want that. So we want it, but it does work well when you're below the speed of light. Then your accelerations are given by this. So the test particle has to move slowly. The planets have to move slowly. But, we're actually going to say the gravitational fields have to be straight up stationary. So these planets really shouldn't be moving at all, right? They're not moving at all. And anything else that might affect the gravitational field has to be constant in time, right? So the density of the planets can't change, for example. The mass of the planets can't change. Although how could it, right? If matter was falling onto the planet and the planets were increasing in size, that matter itself would contribute to the gravitational field even before it fell on it. And as it moved to fall on it, it would be moving, and that would not count as things moving slowly. So I guess what I'm saying is I'm kind of confusing these two together. So I guess when we think of things moving slowly, let's just focus on the test particle moving slowly. And stationary fields, let's talk about that as whatever's the source of the gravitational field, those guys are fixed and nothing's changing with time. So let's zero in a little bit more on these assumptions now that we've sort of expressed them. Weak fields, well, the way we're going to identify weak fields is we're going to write this down. We're going to say that the metric of space-time is very close to the Minkowski metric. There's a coordinate system out there where the metric of space-time is very close to the Minkowski metric plus a little deviation. And this little deviation is such that anytime you square it, we can ignore it, right? So it's a first-order deviation, so that anything that looks like h mu nu squared or HAB times HCD, right? That's equivalent to a quadratic term. Then we would just ignore things like that in our work. All right. So that's actually how we will be defining weak fields. Everything is more or less the metric is basically flat, right? I mean, that is sort of what we're after. The metric is flat. Now, the problem, of course, is that a flat metric is still special relativity, right? So that's not Newtonian theory, right? That's four-dimensional space-time. It's just kind of close to being flat. So this is just an obvious restriction on what a weak field in GR would look like. But it is still true that weak fields in GR, even though it kind of reduces the weakest possible field in GR, would ultimately reduce to Lorentz space-time, it's still going to be the best we can do about a weak field, all right? All right, now let's look at things moving slowly. So we decided this is sort of test particles moving slowly, right? I kind of walked myself backwards out of everything moving slowly, like those planets, right? So this is the test particles moving slowly. So remember, what our test particle is the thing that's being accelerated by these two fields. So in the GR side, the test particle is moving along a world line, and in the Newton side, it's got a vector, acceleration vector given by this gradient, right? Elementary physics here, advanced hyper-thinking super-duper theory over here, right? So, but things are moving slowly. So what do we mean by this? So what this basically means is that, let's see, I'll write it down here, that the derivative of the world line with respect to time, right? The derivative or the change in the spatial coordinates, right? The change in the spatial coordinates with respect to time has to be much less than, I don't like my less than symbols, much less than, oh, it's even worse, damn. Much less than c, the speed of light c. In our units, of course, that's 1. So, but this is our coordinate time, which ultimately is going to be the Newtonian time, because Newtonian only has coordinate time. So I want to write this in terms of the proper time. So the proper time will be dxi d tau, where we're parameterizing the curve, the geodesic curve this thing falls under. We're parameterizing it with the proper time. Then this would be what? D tau dt must be much, much less than 1. So we ultimately end up with dx di d tau much, much less than dt d tau, right? So that is an expression of things moving slowly. It's kind of interesting way of looking at it. The rate of flow of coordinate time. So ultimately, proper time and coordinate time will be the same thing in Newtonian system, right? So that means this becomes dxi, okay, dxi d tau, and this, but d tau and dt are the same. So this is dxi dt, and then d tau and dt being the same, this would end up being 1. So you end up with this expression, right? So that shouldn't be a big surprise. Okay, the last one is what? Stationary fields. So stationary fields is the easiest because ultimately everything goes back to the metric, right? G mu nu. So if whatever the fields are, however we interpret the gravitational field in general relativity, the metric is the source of it. So if the metric has any time derivatives, right, if the partial derivative of g mu nu with respect to, I guess it would be x0 is the way we typically write it, but in the work we're doing here, we're kind of mixing x0 with t a little bit, so we might just call that t for now. That's always got to be 0, right? Every metric element has to have a 0 time derivative, and then everything will be stationary that could possibly be a field. So that's a good way of looking at it. If this is the weak field version, right, this is a constant, so the derivative of that with respect to time is 0, but it does say that h mu nu with respect to t must equal 0. Probably more appropriate is h mu nu comma 0 equals 0, where 0 is the index of the time, of the coordinate time. So this is our stationary field assumption. So now we've kind of mathematized our 3 core assumptions. Other assumptions will arise, but all of those new assumptions are going to actually be traceable to one of these 3, if I recall correctly. So with these assumptions, it is our program to show that those assumptions, at their core at least, are sufficient to take these equations and create these equations. So weak fields, slow-moving particles, stationary fields go from here to here. And so on our next lecture, we will just focus on that. And it's interesting because, we've spent a lot of time to understand the important parts of this equation. And now we've basically burned up 2 lectures just on this constant k, and meaning we just finished a lecture on this constant k, and we haven't even derived it. We haven't even begun. We've just announced our assumptions. We understand this equation, though, but we know that this k, it's all about making the Newtonian limit work, right? It's simply a limiting condition. But going through the Newtonian limit analysis, which is what we're going to do in the next lecture, is totally worth it. I'm going to go pretty quickly. It's still going to take an hour, though. And we're after k. So it's ironic that we're spending all our time in the Einstein equation talking about k, but we understand the rest. Look, it's the curvature of spacetime orthogonal to the 4-vector of your lab. That space-time slice that's orthogonal to the 4-vector of lab. The scalar curvature, that is some number it's proportional to the energy density you see in the lab. That's pretty amazing. Now, that's just one application of this thing, right? That's if you contract this with your lab's velocity, but this gives similar kinds of things for any direction you put in there. And that's what the Einstein equation says. Energy density bends space orthogonal to the direction of inquiry to this specific amount. And buried deep in here is the metric. Deep in here. Remember, this is the Ricci tensor and scalar, which are contractions of the curvature tensor, which are complex derivatives of the connection, which are themselves derivatives, complex arrangements of some of the derivatives of the metric. So it's really tough to extract the metric from this. It's also tough to make these guys, right? To make these stress energy tensors. But that is what the Einstein equation is, and we're going to get at k in the next lecture.